Consider this kinematic word problem. A jet is taking off from the deck of an aircraft carrier. Starting from rest, the jet is catapulted with an constant acceleration of 31 meters per second squared along a straight line and reaches a velocity of 62 meters per second. Find the displacement of the jet. Well, the first thing we need to do is draw a little sketch to interpret what all of this paragraph means. So there is an aircraft carrier. An aircraft carrier is generally on the water. So here's some water on one of the oceans. And we'll draw an aircraft carrier on this water. Yeah, something like this, a flat top. And flat. And we'll give it some office, a tower here, and some smokestack. There's our aircraft carrier. And of course, we're going to need an aircraft itself, an airplane. So we'll draw an airplane here somewhere. Here's a jet, just about ready to take off. And underneath the aircraft carrier right here is a catapult. It's a very strong rope that grabs onto the jet, bottom of the jet here, and it pulls it forward. The idea is to get the jet up to speed before it finally hits the very end, and then it would clunk down into the ocean. Well, we don't want this, so we want the jet to reach flying speed here, and then it will take off. Our question, it says it travels along a straight line, so it's going to go from here to here, along a straight line, along that straight line. This is the section on the jet or on the aircraft carrier that we are interested in. After this right here, the jet will fly. What we need to do here is give this a coordinate system. Which way is positive, which way is negative. Now this aircraft carrier can be on the ocean. It could be traveling west or east and north-south. Generally, it's going to line itself up against the wind. For our purposes, we're going to just simply keep it simple. And we'll draw a compass for a coordinate system here. We'll go east, will be that way. So the aircraft carrier is traveling in this direction, going easterly. And we'll make east positive and going west and then going west negative. So the wind will be coming this way and the ship is traveling to the right, as is the aircraft. And this plane is going positive 31 meters per second squared at an acceleration of plus 31 meters per second squared. So now that we have a little sketch, we understand what this problem is asking us, and we have a coordinate system. Next thing we need to do is look at our equations, our kinematic equations. And here they are. These are the 4 kinematic equations we're interested in for this word problem. You'll notice these variables. This is velocity final, initial velocity, velocity I for initial, the acceleration, the time, and the distance. Next thing we need to do is extract from this word problem what all of these variables are. We're going to extract these variables in terms of these variables right here from this word problem. I'm going to make a list of what is given. I'm going to make this list in terms of the variables in our equation. It says here a jet is taking off from the deck of an aircraft carrier starting from rest. Starting from rest, it means its velocity, its initial velocity here at this location is 0. That's what starting from rest represents. So little letter v represents velocity in our equations. Subscript I is the initial velocity. So initial velocity is equal to 0. It's starting from rest. The jet is catapulted with a constant acceleration. In our equation, the variable for acceleration is the little letter a. So in terms of our equation, this is written, acceleration, little letter a, is equal to 31 meters per second squared, plus. 31 meters per second squared, is going to my right, that's plus or easterly, along a straight line. So it's going to go along a straight line. This is the extent of our equations is going to only to give us the answers we need along this straight line. And it reaches a velocity of 62 meters per second here. Its final velocity then, in terms of our equations, Vf is final velocity. That's what this represents. It reaches a final velocity of 62 meters per second squared. So final velocity, little letter v, is equal to 62 meters per second. And it says here, find the displacement of the jet. Now the displacement in one dimension, this is all in one dimension going across. The displacement is from here to here, that distance. Displacement is simply distance with a direction. So we're asked to find this distance, and the direction we know is going to be east. And in our equations, distance or displacement is represented by the letter x. And when we make this list of given, we have to include what is asked for. In this case, displacement is asked, and x is represents distance or displacement, and that is what we want to find. So we have extracted from the word problem all the variables that we need. Now we just have to find an equation which will fit all of these variables. Or maybe vice versa, an equation where all these variables will fit into. So let's have a look. Here are our equations, and here's our list of 4 variables, and here's our equations. There are 5 variables in total in our equations. One of these equations will work. Let's see what we have. Initial velocity in equation 4, we have initial velocity. Final velocity is also available. Acceleration is also available. And we need time, but time is not part of our given list. So we can't use equation 4. Equation 5 also requires time. So we can't use equation 5. And equation 6 also requires time. Little t represents time. We don't have time in our list. And if we look at the 7th equation, this one has final velocity. Here's final velocity. Initial velocity, we have that. Times, or 2 times the acceleration, we have that. And the distance is what we need. So all of these variables are all in this equation. And this is the equation then which we're going to choose. The other 3 are unavailable to us because we don't have the value of time. So let's use equation 7. The equation 7, and I'll just copy it down here. Equation 7 is little v. Final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the distance. At that distance is also displacement. Displacement is distance with a direction, so we'll just call it distance. Make it simple. So we're going to solve for x. That's what we're looking for, x. We have everything we need now. At this point right here, the physics is done. All that's left to do now is take these numbers, place them into this equation, and solve. So let's do that. Initial velocity squared, or I should say final velocity squared. Final velocity is 62 meters per second, everything squared. That's what that represents, including the units, is equal to the initial velocity squared. Initial velocity is 0. Well, 0 squared is 0, so it'll simply drop out. Plus 2 times the acceleration is 31 meters per second squared. Multiplied by the distance x. All that's left to do here now is algebra. So moving forward, let's remove these brackets on the left-hand side. This 2 operates on the number 62, operates on the meters, and it operates on the seconds. In order to remove that bracket, it would look like this: 62 squared meters squared per seconds squared. We cannot ignore the units. They're just as important as the numbers. Is equal to, well, 0 squared, that just drops out. And we have 2 on the right-hand side, multiplied by 31 meters per second squared times x. What we need to do here is isolate x. Everything here is multiplied. We don't generally write down the multiplication symbols like this: 2 times 3 meters per second squared times x. That's a multiplication sign. That can be done. It's a little messy. But as long as everything here is together like this, it's all multiplication, just like it is here. 2ax, that's all multiplied. So if everything here is multiplied, the opposite of multiplication is division. Oh, this is, oh, my mistake. 31, I thought there was something wrong. 31 meters per second squared. 31. So let's multiply the 2. It's a constant, so we'll just multiply it across. That gives us 62 squared meters squared divided by seconds squared is equal to 2 times 31, 62 meters per second squared times x. In order to isolate x, we're going to have to divide both sides by 62 meters per second squared. Remember, this is one number. Wherever the number goes, the units follow. Dividing both sides by 62 meters per second squared, it would look like this. Let's say we have this equation. I'm just going to divide here 62 meters per second squared and divide all of this on the right-hand side by 62 meters per second squared. All of these will cancel out on the right-hand side. Effectively moving it to the left-hand side is equal to x. Cleaning this up a little bit, 62 squared meters squared per second squared divided by 62 meters per second squared, just moving it over here, is equal to x. X is the distance that we are looking for. This looks rather easy. Division 62 squared is 62 times 62 divided by 62. So one of these 62s here will cancel out. And that would leave us 62 here. And this is 62 times 62. So one of them will cancel out, leaving us with just 62. And looking at the units, we have in the numerator, we have meters squared per second squared divided by, well, 62, they cancel out, but they still have 1 left over. 1, and looking at the units, meters per second squared is equal to x. And we got to look at the units as much as you look at the numbers. Now let's operate on these units. We know that the final number is 62. 62 divided by 1 is 62. But looking at these units, they need to be reduced. And what this is a fraction divided by a fraction. Like this. Here's a fraction. There's a numerator, denominator, big division sign. Something like this. 1 quarter divided by 1/8. Fraction divided by a fraction. And the way this is done, you take the denominator, invert it, and multiply the numerator with it. So it becomes 1 quarter times, take the denominator, invert it, and multiply. 8 over 1 is equal to, multiply across, 8 divided by 4. 8 divided by 4 is equal to 2. With this, it's exactly the same thing with the units. So here's a fraction, and here's a fraction. They just happen to be letters instead of numbers, but it's still a fraction and a fraction. And the way to divide this fraction with this fraction is exactly as I did here. Leave the numbers alone. So let's look at the units themselves. So it's meters, the numerator, meters squared, divided by seconds squared. Take the denominator, invert it, and multiply, times seconds squared divided by meter. And this equals to the seconds squared and the seconds squared cancel out. 1 meter down here, there are 2 meters here, meters squared. This is written meters times meters, that's meters squared. So 1 meter and one of these meters cancels out, leaving us with just 1 meter. So when this is done, the unit is meters. Now that we've done all of this, this is equal to, we have 62 divided by 1, which generally isn't written down, and the units comes to meters in the numerator, 62 meters. And since this is displacement is a distance with a direction. The distance with a direction, and we know it's going east, according to our coordinate system. Therefore, the answer for displacement is 62 meters east. Find the displacement of the jet. Therefore, displacement, or the distance traveled with a direction, that's what displacement is. Displacement is 62 meters east.